Hello everyone, welcome to the channel Statistica Hub. So in previous lecture we have studied the concept of kernel and image of linear mapping. So in this one we will see the kernel and image of matrix mapping. Matrix mapping. What will be the case here in the matrix mapping? Okay, so how our matrix mapping is defined as there is a matrix of A m cross n and which is on the mapping t r's power n to r's power m, and which is defined as that t of x equals to ax. Ax. This is our mapping, matrix mapping. Now, if I say that I have this matrix of A2 cross 3, which the corresponding elements of this matrix are 1, 2, 2, 4, 3, 2. Okay, and the mapping goes as r's power cube to r square. Okay, and now let's just consider the standard basis of the standard basis vectors of R cube. What are the standard basis of this? It will be E1, E2, E3. Okay, now if we look to the images of these basis vectors, I want to find the images of these basis vector. The images of this basis vector can be found like this, which is T of E1. The image of E1 would be T of E1, that will be A E1. Similarly, T of E2 equals to A E2, and T of E3 equals to AE3. So these are the corresponding images of these basis vectors. These basis vectors. Okay. Now we have studied a theorem which says that if I have a mapping which is TV to U, we have studied this in the previous lecture, that this is the mapping which is a linear mapping, and there are basis vectors of u which is alpha 1, alpha 2 to alpha n. These are the corresponding basis vectors of v. Okay, then the corresponding images of these basis vectors defined as t alpha 1 to t of alpha n, they would generate u. They would generate image of t, actually image of t, sorry, not u. They would generate image of t. Okay, now applying this only here, we got that we have our basis vectors. We have our basis vectors as e1, e2, e3, and these basis vectors are spanning my vector space R cube. Okay, and the corresponding images of these basis vectors, which are a e1, a e2, a e3, are spanning the images of A. Okay, what did I say? That this image, that the a e1, a e2, a e3, sorry, I can write it as span of TE1, TE2, TE3. They are they are spanning my image. They are generating my image set of A, image of A. Okay, by this theorem. Okay, now what are these vectors? These vectors, these corresponding vectors are my columns of A. These are corresponding columns of A. How can I say that? That if I compute these vectors A E1, let's just compute it, then 1, 2, 2, 4, 3, 2, and multiply it by its E1, which is 1, 0, 0, then it would give me 1, 2, which is our first column. Okay, and if I compute A E2, which is multiply this matrix by 0, 1, 0, then this would give us 2, 4, which is our second column. And similarly for AE3, this would give us, if we multiply this by E3, which is 0, 0, 1, this would give us 3, 2, which is our third column. So the corresponding images of these basis vectors are actually our columns of A. Okay, and from this we can see that the images of A, are precisely the column space of A. What? That the image of A are the column space of A. Okay, now this is a very important result. How can I say this? Because we have studied the concept of column space, that if I have this matrix and these are the, let's say, three columns of this matrix, then I'll consider the set of these columns. That there is a set S, which is the set of these columns as C1, C2, C3. These are the set of the column vectors. Okay, This is the set of column vector. Then the column space of A is defined as the span of C1, C2, C3. That's how we can define the column space of A. And that's what it is here. It is happening here that I am spanning TE1, TE2, TE3. This is generating my image space of A. And what are these? These are the corresponding columns of A. So these are the column. So this will form the column space of A. So from this I can say that the image space of A is the column space of A. Okay. Now if we look to the kernel part, then the kernel part here is that my kernel part, which is that the kernel is defined as, let's say, W, which is equals to x belongs to r cube. All those values of x, as our transformation is defined for matrix mapping is ax, then for all those values of x where ax is equals to 0. Okay, then this is called the solution space. Okay, so what is this ax equals to 0? Ax equals to 0 is actually the homogeneous system. Okay, it is a homogeneous system. Okay, so we are actually saying that the kernel of A and the corresponding solution of this homogeneous system is said to be the solution space of the homogeneous system. The values of x is, okay, the values of all the xi's are the corresponding solution of this homogeneous system. So from this there is an important result, which is this, that the kernel of this matrix A is the solution space of homogeneous system Ax equals to 0, and which is also called null space of A. Null space of A. Okay, so from all this we got two results. Which is as that if I have a matrix of A m cross n over, let's say, field K over K, and the mapping A is defined as R k's power n to k's power m, then the corresponding kernel of A is defined as null space of A, and similarly the image of A is defined as column space of A. Okay, now this is a very important result. Okay, now if we look to the part of rank and nullity of linear mapping. Okay, what? Rank and nullity of linear mapping. Linear mapping. Then if the linear mapping goes like T V to W, this is our linear mapping. Okay, now the rank of T, what? The rank of T or rank of this mapping is the dimension of its image. Dimension of its image, that is the dimension of image of T. Okay, and the nullity of this transformation T is actually defined to be the dimension of kernel of a T, which is dimension of char T. Okay, this is how we can define the rank and nullity. Okay, now there are results of this results. There are two important results for the rank and nullity, which are as that let V be a finite dimensional vector space. Okay, V be a finite dimensional vector space, and where the linear mapping T V to W is defined as like this, and this is our linear mapping. Then dimension of V is equals to dimension of char T plus dimension of image of T. Okay, or you can also say that which is equals to nullity of T plus rank of T. Okay, so what are we saying here, that what is dimension of V? Of V is actually the number of basis vectors in V which are generating the whole vector space V. Okay, so dimension of V is that, and that the dimension of V is actually the sum of dimension of char T and dimension of images of T. Okay, and the second result is as that let V and W, we have two vector spaces V and W which are our finite dimensional vector spaces. Okay, finite dimensional vector spaces, and these two vector spaces have same dimension over the field F, and the mapping is as TV to W be a linear mapping. It is a linear mapping. Mapping. Then then T, the mapping is 1 1 implies that the mapping is onto, and similarly the mapping is onto implies the mapping is 1 1. Okay, let's just see it how. So let's just first consider that my mapping is 1 1. When I say that my mapping is 1 1, this will be only possible that if my char t is equals to 0. We have studied this in the just previous lecture. Okay, this will only be possible when my char t equals to 0. Char t is equals to 0. It implies that the dimension of char t is equals to 0. Okay, now using this, we got that the if we apply it here, that the dimension of v is equals to dimension of char t plus dimension of image of t. Okay, now I see that my dimension of cat is equals to 0, so this would be 0. What will I get? That my dimension of v is equals to dimension of image of t, and it is given in the theorem that it is a that v and w are finite dimensional vector space of same dimension, that it means that the dimension of v is equals to the dimension of w. Okay, so from this I can see that the dimension of v is equals to dimension of images of t, which is equals to the dimension of w, because dimension of v is equals to dimension of w. Okay, so as image of t is the subspace of w, image of t is always the subspace of w. So from this we can see that the image of t, that the dimension of image of t is equal to the dimension of w, as these both have the same dimension, that the dimension of image of t is equal to the dimension of this vector space w. So from this we can say that t, which is my mapping t, is onto, as every element in the vector space w has its pre-image. Okay, because they have the same dimension, the image set and the vector space w. Okay, now second case, let's just consider the second case when I consider that my mapping is onto. So when our mapping is onto, it means that the image dimension of image of t is equal to dimension of w. Okay, now similarly by using here using this formula, that dimension of v is equals to dimension of clarity plus dimension of image of t. Okay, now by applying this, that dimension of image t equals to dimension of w. So this would give me dimension of w, and we have also seen that the v and w vector spaces have same dimension. The dimension of v equals to dimension of w, so this will be dimension of w because they have same dimension, so they will cancel out. From this I got that my dimension of char t is equals to 0. That means my char t is equals to 0, and my char t is equals to 0, it means my mapping is 1 1, that t is 1 1. Okay, so we can see that if I have two vector spaces which are finite dimensional vector spaces of same dimension, this is very important. This is the only case when this is only be possible when they have same dimension. They have same dimension. Okay, over the same field F, and the matrix mapping is linear, then the mapping is 1 1 implies mapping is onto implies mapping is 1 1. Okay, now let's just look these all these results, apply these results in an example. Okay, so let's say this is our mapping for A, which is as r's power 4 to r cube, and my matrix is defined as 1 1 3 2 3 8 3 5 13 and 1 minus 2 minus 3. Okay, this is my matrix A. Okay, now I want to find the basis and dimension of char A and images of A. Okay, I want to find this basis and dimension of char A and images of A. Now we'll apply the previous results that the column space of A is equal to the images of A. What we have studied that column space of A is equal to the images of A. Okay, and we have also studied that the kernel of A, is the solution of homogeneous system AX equals to 0 in the term in the matrix mapping. Okay, so let's just apply this for first, that the column space of A is equals to the images of A. Okay, now as this is the column space of A and we have the matrix A, so let's just take a transpose of it, then row reduce it. Okay, and then we reduce it to the row reduced echelon form. Okay, so just take a transpose of it, which is 1 1 3 2 3 8 3 5 13, and is it 13 or is it 15? Okay, it is 13. 1 minus 2 minus 3. Okay, this is my transpose of it. Now we'll just reduce it to the row reduced echelon form. I am just the point of transpose of taking transpose of this matrix A is that only that there it is given of here column space of A, and I am going to apply the row transformation here. So just for uh, not applying the column transformation, I am just transforming this matrix to the uh, into the column format so that I can apply the row transformation. So from that I can get the column space of A, the corresponding basis vectors for the images of A and the corresponding image vectors. Okay. So let's just row reduce this matrix to the echelon form by applying the transformation, which is 113. Let's apply here, which this would give us multiplying this by 2 and subtracting this. That's, I can write it only. R2, by applying R2 is R2 minus 2R1, and in R3 we'll apply R3 minus 3R1, and similarly in R4 we'll apply R4 minus R1. Okay, so this would give us 0 1 2 0 2 4 and 0 minus 3 minus 6. Okay, apply another, which is in R3 we'll apply R3 minus 2R2, and in R4 we'll apply R4 plus 3R2. Okay, this would give us 1 1 3 0 1 2 and 0 0 0 0 0 0. Okay, so from this I got that 1 1 3 and 0 1 2. These are my corresponding bases of images of image of A. These are my corresponding basis of images of A. Okay, and the dimension of this image of A is equal to 2. Okay, similarly, if we look to the kernel part, then the kernel of A, then the kernel of A is defined as the solution space of the homogeneous system AX equals to 0. Okay, now let's just apply it here. Let's just take our X as X, Y, Z, T. XYZ vector. Okay, then reduce it this A to the echelon form. So if I reduce this A matrix to the echelon form, it would give me 1 2 3 1. Apply in this first transform, which is R2 minus R1, and then R3 would apply R3 minus 3R1. This would give me 0 1 2 minus 3. Okay, and this will be 0 0 0 0. Okay, and what did I have? I have to apply Ax equals to 0. Ax equals to 0. And what is my x? X is my x, y, z, s, t, which is equals to 0 vector. 0 vector. Okay, now from this I got the equations as x plus 2y plus 3z plus x plus okay, this is z, this is t, no s, plus t equals to 0. Okay, and the second equation is y plus 2z minus 3t equals to 0. Okay, so from this I got y equals to 3t minus 2z, and my x equals to, if I substitute y here, I got uh, 3 60 60 70, which is minus 70, and plus z. Okay, so my x is equals to this. So from this I got two free variables. I have free variables which are z and t. I have these two free variables, z and t. So from this I got that my dimension of cat t is equals to 2, because I have two free variables. And for finding the basis of this kernel of A, we'll just put the values of these free variables, which is z. If I put z equals to 0 and t equals to 1, I got my basis vector as, uh, I just put here, and this would give me x equals to minus 7, and y equals to 3, and z equals to 0, z equals to 0, and y equals to 1, t equals to 1, so it would be 1 equals to 1. And if we'll put z equals to 1 and t equals to 0, then our second vector would be 1, and what is the value of y? Value of y will be minus 2, and this would be 1, and this is 0. Okay, so that's how we can find the basis and dimension of kernel of A and images of A. Okay, now let's see further. Okay, now we'll see the concept of singular and non-singular linear mapping. Linear mapping. Okay, so what are singular and what are non-singular linear mappings? So let's say this is my linear mapping TV to U. This is my linear mapping. Linear mapping. Okay, and in linear mapping we know that every zero vector maps to the zero vector. Okay, now this mapping T is singular. This mapping T is singular if image of some non-zero vector v is 0. That means I say that if there exists a vector v which is not equals to 0, which is non-zero, such that the image of this non-zero vector is equals to 0, then we can say that my matrix is singular. Okay, when when I have some vector which is non-zero and whose image is 0. Okay, and my mapping is T is non-singular. Non-singular if 0 vector is the only vector whose image under T is 0. Okay, that is T0 equals to 0. T0 equals to 0. That means 0 vector is the only vector whose image under T is 0. That means if char T equals to 0, and when char T equals to 0, T is invertible when non-singular. Okay, so my mapping is invertible when it is, in this case my mapping is invertible. Okay, okay, now there is an important result from this invert singular and non-singular case, that if I say that my mapping is non-singular, if I have the non-singular linear mapping, then the image of any linearly independent set is linearly independent. What did I say? That if this is the mapping TV to U, which is non-singular, non-singular, non-singular linear mapping, and then the images of, then this is a result. Okay, then the images of any linearly independent set is linearly independent. Okay, it is similar, it's similarly saying that we have that if my cat equals to 0, non-singular means that my cat equals to 0, and we have studied this previously, that if my cat equals to 0, then the images of linearly independent set of vectors, let's say alpha 1 alpha 2 to alpha n, any alpha 1 alpha 2 to alpha n in V are linearly independent. Okay, we have studied this earlier in our very first theorem. Okay, so let's just see it here, that when I say that I have a non-singular linear mapping, then it means my t0 equals to 0 is the only case here, is the only vector which are mapping to 0. Okay, then let's consider that the dimension of v is equals to n. Dimension of v is equals to n. Okay, then as these are linearly independent, so let's consider that e1, e2 to en are the standard basis vectors of this linearly independent set in V. Okay, now for this linearly independent set, these are linearly independent, there exist scalars such as alpha 1, alpha 2 to alpha n, such that we have alpha 1 e1 plus alpha 2 e2 to alpha n en, that the linear combination is equals to 0, and as these all are linearly independent vectors, we will have all our alpha is equals to 0. Okay, 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 because it is linearly independent. Okay, now if we'll see the corresponding images of these vectors, that is te1, te2 to ten, these are the corresponding images of these vectors. Okay, now I want to find the whether these images vectors are linearly independent or not. Okay, so for checking their linear independency, we'll just write in them in the linear combination. Let's say for the alpha is alpha 1 te1, alpha 2 te2 to alpha n ten equals to 0. So if the in this linear combination all the alphas are equals to 0, then we can say that the corresponding images vectors are linearly independent. Okay, now I can write it as T of alpha 1 e1 to alpha n en by the application of by the properties of linear transformation. Okay, and we have got that alpha 1 e1, alpha 2 e2 to alpha n en equals to 0. That means that means t0 equals to 0, because my t is non-singular. What? My t is non-singular. T0 is equals to 0 is the only property that has to be satisfied. That this is the only case found here. So for this to be satisfied, this has to be 0. That alpha 1 e1 plus alpha 2 e2 to alpha n en has to be equal to 0. Okay, so from this is this corresponding same equation. So from this I got that as these vectors are linearly independent, I got that my all alpha is equals to 0. So from this we can say that the corresponding images vectors te1, te2 to ten are linearly independent, are linearly independent. Okay, now similarly, if we'll consider that we have studied the concept of isomorphism earlier, that in the isomorphism case, if we look at the isomorphism, when I say that I have two finite dimensional vector space, let's say V and W, we are two finite dimensional vector space over F, then these are said to be isomorphic over F, then these vectors are said to be isomorphic over F if they have same dimension, that the dimension of V is equals to dimension of W. This is the theorem that we have studied in the isomorphic topic. So we can also form this as in the terms of singular and non-singular, that if my V is a vector is finite dimensional vector space and the mapping is as TV to U, which is linear. Okay, and the dimension of V is equals to dimension of U. Okay, then dimension of U, then T, the mapping is isomorphic imply if and only if T is non-singular. Okay, the mapping will be isomorphic if T is non-singular, and if T is non-singular it will be isomorphic. So this is like converse true, its converse is also true. Let's just check it here. Okay, so for checking this, let's just consider the one case. So for none, say for the isomorphism, we have isomorphism when it is bijective. Okay, bijective means it is 1 1 and on 2. Okay, so let's just check for 1 1 case. If I say that my mapping is, let's just consider it here. If I say that my mapping is 1 1, if my mapping is 1 1, so if my mapping is 1 1, then t0 is equals to 0 is the only case that I have. Okay, that means I didn't have any vector in the mapping which is mapped to 0 vector. Okay, as 0 is the only vector which belongs to V and can map to 0 which belongs to the u vector. Okay, so from this I got that t is non-singular. T is non-singular. That's what the definition of the non-singular is. That I have 0 as the only vector which is mapping to the 0. Okay, so our 1 case is satisfied here. Okay, now if I consider that my t is onto, what will be the case that time? Okay, onto case. T is onto. Okay, now let's just consider that my dimension of v is equals to n. Okay, so if my dimension of v is equals to n, then the standard basis of these standard basis of y will be e1, e2 to en. These are my corresponding basis vectors, and these basis vectors are linearly independent. Okay, and as my mapping t is non-singular, my mapping t is non-singular, then the images of this linearly independent set would also be linearly independent. Okay, so I am saying that my image vectors, which is t e1, t e2 to t en, they will also linearly independent. Okay, now we have to prove that every element in u, every element in u, okay, has a pre-image in v. Okay, that's when we can prove that it is onto. Okay, now if a set, let's say there is a set which is spanning our vector space v. Okay, then its image would span image of t. Okay, I am saying that there is a set which is spanning vector space v, then its image, then the corresponding images of this vector space would span image of t. Okay, so let's just consider that if I have a vector u which belong to u, this u, okay, image vector, then u, the corresponding images of with then the corresponding images of these vector spaces are spanning my images of t. Then these vectors will as these vectors are spanning my images of t, so I can write this vector u as alpha 1 t e1 to alpha and ten in the linear combination of this u vector, in the linear combination of this u vector, as these vectors are spanned by are spanning images of t. I am so sorry about this. Okay, so I, by the property of linear transformation, I can write it as alpha 1 e1 to alpha n en. Okay, and this alpha 1 e1 alpha 2 en is the vector which belongs to the vector space v. Okay, so from this we can see that every vector in U, that every vector in U has a pre-image in V. Okay, has a pre-image in V, as this is the vector V, because these are the corresponding bases. Then if there is a vector V which belong to my vector space V, then this vector V can be written in the linear combination of this basis vector, and this is what we're doing here. This is the linear combination of these basis vectors. Okay, so my t v equals to u. Okay, so from this we can see that my every vector in u has its pre-image. That means I got t is 1 1, t is 1 1, and my t is onto. Onto. That means it is isomorphism, because it is bijective. Isomorphism. Okay. So we got that if there is a mapping which is linear and they both have same dimension, then the mapping is isomorphism if and only if the mapping is non-singular. Okay. Now, let's just do an example of it. Like, mm, there is a linear operator. I want to find the linear operator t. Sorry, there is a linear operator which is on R cube, defined as t of x y z equals to 2x 4x minus y, 2x plus 3y minus z. Okay, this is my linear operator on t. Now I want to find the t inverse and t square and t inverse square. I want to find t inverse, t square, and t inverse square. How can we find this? Okay, so for finding the t inverse, let's say this is my t x y z and the corresponding with r s t. This is my t x y z. Then the corresponding inverse of this would be t inverse r s t is equals to x y z. X y z. Okay, so we'll just write it as that 2x 4x minus y by this minus y comma 3x 2x plus 3y minus z equals to r s t. Okay, that means 2x equals to r, 4x minus y equals to s, and 2x plus 3y minus z equals to t. So from here I got x equals to r by 2. Okay, and from this I got y equals to 2r minus s, and z equals to r plus 6r minus 3s plus t, which is equals to 7r minus 3s plus sorry minus t. Okay, this is also minus t. So what is my t inverse? My t inverse a of rst, my t inverse of rst is equal to 1 by 2r, 2r minus s, 7r minus 3r minus t. This is my t inverse. Okay, and I can also write it as t inverse of x, y, z is equals to 1 by 2x, 2x minus y, and 7x minus 3y minus z. Okay, that's how we can find the inverse. Okay, now if I look to the t square, if I want to find the t square, okay, then it means apply the transformation t twice. Okay, so t square of x y z, that means that I have to apply the transformation t on t of x y z. That means t of 2x 4x minus y, 2x plus 3y minus z. Okay, so if I apply the transformation here, it would give me, because t of x y z equals to this, then x 2x. Okay, so it would give me twice of x. This would be 2 of twice of x, and second would be 4 of twice of x. I'm just applying the transformation here for these values 2x, 4x minus y, and this. Okay, and 4x minus y, comma, and the third term would be 2 of x plus 3 4x minus y minus 2x plus 3y minus z here, because here are x y z are this x y z, these are the full terms, and I'm putting the value of x as like this, that my x is 2x, and here I'll put 2x, and for the y I'll put 4x minus y here. Okay, so just putting the values here, and then I got t square x as 4x, comma, and this will give me 4x plus y, 4x plus y, okay, comma, and this would be 4x, 12x, and minus 2x. This will be 14x minus 6y, and plus z, plus z. Okay, this is my t square. Okay, now if we look to the inverse of t square, if I want to find the t is power minus 2. Okay, so for that it means apply t inverse twice. This is my corresponding t inverse, and I have to apply t inverse twice. That means t inverse square equals to t inverse of 1 by 2x, 2x minus y, 7x minus 3y minus 2. Okay, now I'll just apply the transformation here, that I have to put the value of x as 1 by 2x, and here, and for y I have to put, 2x minus y, and similarly for z I have to put 7x minus 3y minus 2. Okay, so let's just apply here. So 1 by 2 x, it would give me 1 by 4x. Similarly, 2 of 1 by 2x minus 2x minus y. And the third term would be 7 of 1 by 2x minus 3 of 2x minus y minus 7x minus 3y minus z. Okay, let's just simplify it. So after simplifying, we got, let's just write it here, 1 by 4x minus of x plus y, comma, let's just simply calculate it. This would give me minus 3 to the 6, 7 to the 14, and it would be minus 19. Minus 19 by 2x plus, so this would be 6y. 6y plus z. Okay, so that's how we can find the corresponding transformations. These are the corresponding transformations. Okay, that's how we can find them. So for today, I think it's enough. So I just meet in the another lecture. Thank you for now.